Okay. Hello, everyone. Good morning, good afternoon, or good evening to everyone all around the world. Today we have a third webinar, AM Smart. For today, I'm very happy to introduce my colleague, Professor Huang from Singapore University. He's going to lead this session. I hope you enjoy the meeting today and also webinar, learn about whatever going to be discussed today. And thank you also for both speakers accepted to present today. And yeah, that's all. Professor Wyman, floor is yours. Go ahead.
Thank you very much. Good night, good morning, and good afternoon. It's great to have this particular webinar, and tonight is more about shared memory materials, shared memory polymers in particular. And we have two speakers here. The first, Professor Xiao, he's going to talk about the modeling of shared memory effect in polymers. And the other is Professor Yang. He's going to discuss about the 4D printing of shared memory biodegradable scaffolders. So I hope that everybody will enjoy these two great speeches. And let's welcome the first, Professor Xiao from Zhejiang University, China. Let's welcome. And Professor Xiao, now it's your turn.
Are you listening to me?
Yeah, you have 20 minutes. Yeah, 20 to 25 minutes.
Okay. So you give me 1 minute. I need to log in because my system do not think I need to restart. But wait a minute.
Okay.
Shall we start with Professor Keke first? If it can, would be helpful and save the time?
Yeah, is that possible? Professor Yang, are you ready? If that is possible, then you start first.
No, I'm first to share.
Yeah, okay, yeah.
Okay.
Yeah, thank you. So now we have the first speaker. We have to swap the sequence. Professor Xiao got a little bit of problem with his computer, and so that we'll start with Professor Yang. Is about 4D printing of shared memory biodegradable scaffolder that is from Sichuan University, China. Let's welcome.
Okay. Thank you, Professor Huang. Good evening or good afternoon. I'm Keke Yang from Sichuan University. And at first, I great appreciate Professor Huang and Dr. Mertua and for the kind invitation and give me this opportunity to communicate with the research in the area of shared memory polymers. And today my topic is 4D printing of shared memory biodegradable scaffold. And at first I will give 1 or 2 minutes to introduce our university. And Sichuan University is located in Chengdu, the very famous tourist city in southwest China. And it's also very famous for its modernized and also inclusive of the traditional culture. And then it has the biggest giant panda base in the world. And our university have a history of more than 120 years, and it's merged from 3 former universities. And now it has 3 campuses, Huaxi, Wangjiang, and Jiang'an. And Sichuan University is one of the most biggest university in China. It has a comprehensive discipline, covered 12 categories, and have 34 colleges and over 60,000 students, including undergraduate students and master and PhD students. And our laboratory named the National Engineering Laboratory of Eco-Friendly Polymer Materials, and the research field of our lab including flame retardant polymeric materials, bio-based and biodegradable polymer materials, and also recycling of the polymer materials. And my personal research interest in focused on the biodegradable polymers and shared memory polymers and also safe cleaning materials. And today I focused on the SMPs. We engaged in the SMPs more than 10 years, and this slide shows some recent publications, and including we developed some SMPs based on the dynamic interactions and also multi-response
SMPs and the composites. And recently we also tried to develop some functionalized SMPs, for example, shape and color changed materials and also shape memory biomaterials. And today I will introduce these areas of my recent work. As we know, the SMP, because they have distinct shape change capacities and make it greater potential in the biomaterials. And after decades of the development, different kind of the biomaterials has been reported by researchers, for example, for the self-tightening sutures and occluders and other dendritic materials, and also some different kind of stains or the scaffolds. And also, they recently rapidly developed of the 3D printing technology, also bring the great convenience for the fabrication of biomaterials, and it can easy to produce in a multi-scale or with multi-materials and also multi-functionalities, and also to adapt to the different metrics of the SMPs and the also the special demand of the applications. Diverse printing technologies has been employed in this area. For example, the FDM, also SLAs and the DFW and so on. And our strategy, and we try to intend for the different applications, for example, the protective devices or stand or scaffold, and also based on our previous research background. Here we choose the aliphatic polyesters to serve as the matrix of the SMPs. Here we choose the PLA and the PCL or PPDO, and also the PBF with the unsaturated double bond on the repeat units, and also to adapt to the different metrics. Here we also choose the different printing technology, and for example, we can use the facile FDM printing technology to printing the linear components. But however, this FDM printing technology also has some shortcoming because they have a weak bending strength between the layers. So we also introduced some photosensitive group into the linear component polyesters, and then we can print in the materials with the UV assisted FDM technologies, and then we can obtain the printing object with more stable structures. And the first example I will introduce is a 4D printing bioactive Huang scaffold. From the design strategy here, we choose the crystalline PCL segment to act as the switching segment, and the melt temperature of the PCL can be tuned to near the body temperatures. And also we choose another segment of the PBF. It contains the double bond in the repeating units, and it can serve as a photocrystalline sheet during the FDM printings, and it can serve as a net point for the SMPs. And another important reason we choose the PBF is it's reported to be a segment can promote the osteogenesis, so we can use it a good candidate to develop the bioscaffold. And for the preparations, here we use the PPF diode and the PCL diode and coupling with it to linear components, and it can easily produced by the FDM printing technologies. And with the FDM, we also use the UV irradiations. The printing object can form the network, and this resulting to the network can shoot the tunable mechanical strings, and it in the range near the bone mechanical performance, and allow it candidate to produce the bone scaffold, and also to increase the line behavior of the PCL segment also can be tuned, and after optimize its composition, we can get the network with good shared memory fits. And then we also evaluated the 3D printing abilities of these copolymers. Besides the field densities, also the composition will affect the porosity of the scaffold, and if the PBF is increasing the PBF segment, the printing and accelerates accuracies will be decreased. And based on this, optimize the structures and get printing the bone scaffold. And we also tested the binding strength of each layer of the printed object, especially with the UV irradiation. We can find that the anisotropic of the mechanical property has been modified, and especially in the vertical directions, like the printing directions, and we can find that the tensile strength has been enhanced obviously. That means the binding strength of each layer has been enhanced. And we also tested the flame work stability of the scaffold to put it in the PBS solutions. We can find the printing object with the UV irradiation. They show much better stabilities in the water environment. And the SEM of this, the shared memory effects of the printed scaffold also can show the good potentials in the minimal invasive implantations. Here we first printing the scaffold with an irregular shape, and you can use it programmed and formed in a small size, and you can print it in printing through a small notch, and then we can trigger it recoveries by heating, and it can perfectly adapt to the defect surroundings, and the bending strength also greatly improved compared with the unprogrammed ones. And also we evaluated the cytotoxicity and the seal adhesions of this scaffold. We can find the CCK8 assist showed its good biosafety, and the seal density was increased with the introduce of the PPF segment, and also showed the upper grade after regulated the RNA expressions and the ARP activities. And we can find, especially compared with the control group, the sample, the PX4 and C6, and showed the best infection with a significant upregulated ARP activities. And also we evaluated the in vivo effect on the bone repairs. Here, most cranial defect models has created, and we first deformed this scaffold in small scales, and you can easily implant in the defect. And when we heat it, it can
trigger its recover to its original shape and fit the defect within a short time, only 12 seconds. And after the implantation for 4 weeks, we can find that more bones was generated from the edge of the defect to the middle, and compared with the blank ones, it's much better bone repair effects. The second example here we'll introduce is a 4D printing scaffold with the hierarchical structures. And in order to create the hierarchical structure on the materials, here we first design the ternary copolymers. And in the first step, we random copolymerized the air nectide and the caprolactans to get a random copolymer with tunable glass transition temperatures and also near the body temperatures. And it also can act as the switching segment. And for the fixed segment, we here introduce the PPDO. It's crystalline with a higher metal temperatures. And these multiple block polymers should distinct microphase separation morphologies, and that allow to create hierarchical structures. First, we can produce by the FDM printings to get the microporous scaffold, and then we can put it in the Archi solutions to accelerate the degradation due to the microphase separation morphologies. And it can also show the different degradation rate that we can create the microscale porous on the scaffold. Then it can show the enhanced bioactivities in this scaffold. And after 2 steps of the synthesis, we can characterize the structure, and we can find the mechanical property of this copolymer also can be tuned by the composition, and also tuned its glass transition temperatures and also the crystalline behaviors. And based on the optimized composition, we can find this material components can show the good shape memory effects. Then we use the TM to observe its microphase separations morphologies, and can show the distinct phase separations. And based on these characters, we can find we can put it in the Archi solutions, and we can find the PPDO segment should a much faster degradation rate, and PLC should a slowly degradation rate. And then in the copolymers, we can find the surface can create micro-scaled porous structure. And we also can be identified this porous structure by the LCSM to evaluate its roughness on the surface. Then we printing by the FDM, and we can printing the original porous scaffold, and then we put this scaffold in the Archi solutions and accelerate its degradation, and we can find the surface will appear the microscale porous, and that we can get the hierarchical structure porous scaffold, and it can shoot the good shape memory effects, and with the regular scaffold, it can recover to its original shape. At last, we also evaluated the shear adhesion ability of these copolymers,
and we can find compared with the material with the smooth surface, and can roughly surface can show much better seal adhesions, and it had the denser and longer thinner areas on the surface, and also the cell separation areas is increased compared to the controlled group. And also we can find that this roughly surface can show the significant increased PFA case. And this system, the further evaluation in the in vivo evaluations has also still ongoing, and here we are not sure the results. And at last, briefly summaries. In the system, first examples, we introduced the PBF segment into the PCR polymers that not only can show the cross-linked seat for the SMPs, also it can show the enhanced osteogenesis. In the second system, we can find we can create the well-defined hierarchical structures by the microphase separation morphologies, and this allows to show good balance between the desirable shape memory effects and adaptable mechanical performance, and also enhanced bioactivities. And at the last, I will thanks for this financial support of the NSFC of China, and also the project from Sichuan University, and also great thanks for the Professor Lei Xiaoyu and also Dr. Lin Yin Shi. They are the contributor for our work, especially Professor Yu. He helped us to finish all the biological evaluation of our system, and also thanks for my students to contribute for this work. And thanks for your attention.
Okay, thank you very much, Dr. Yang. And now it's time for Q&A session. So, any question from the audience?
May I also ask a question, if you don't mind?
Sure.
Okay, thank you. Thank you very much for your presentation, Professor Yang. And I would also ask if you have any question, please write it in the chat. We can read it loudly here in the meeting, and then we ask Professor Yang also answer your question. Same also for the next speaker. It was a very interesting presentation. Thank you for that again. My question is about the type of the SMP you use in your study. I can imagine there are different factors have impact on your polymer selection. So, of course, something related to biocompatibility, or for example, the type also that type of the stimuli you want to apply for that. Could you a little bit elaborate on that, and what things are very important, and what type of polymer you use in your research?
Sorry, the internet is not very good. The last sentence I missed your questions. Sorry, would you speak again?
Yeah, sure. I was just asking you about the type of the SMPs you are using in your research, because I could imagine there are going to be a different type of factors have impact on polymer selection, like biocompatibility or type of the stimuli you want to active the polymers. Could you elaborate on that, please? I hope you could hear my voice on my question.
Sorry,
I'm not sure about the question about them. Our laboratories is most focused on the design of the polymer, shape memory polymers, and for the biological evaluations is evaluated by another professor, Professor Lee. He is focused on the biological evaluations, and after the result, he has conducted and then tell me what we can regulate my polymers and
and this is the way you choose the polymer, and you can use it in the next step, right?
Yeah.
Okay. And have you ever had any experience with multifunctional polymer that can be activated at more than one stimulus?
More than one signals?
Yeah.
We have synthesized different shape memory polymers. We can respond to the different, for example, heating, mostly near the body temperatures, and also we will try to find some can be respond to the near NIR light. This is two signals for the shape memories applied for the biomaterials. But for the other, we can choose more responsibilities of for the light or the electrical or the magnetic field, and also some of the other systems.
Okay, thank you. Thank you for your answer.
We have someone here raise a hand. Can you?
So can you hear me now?
I can hear. Great.
Yeah, perfect. Yeah, thank you for your nice presentation. According to slide number 12, I was wondering why the material behavior, especially the mechanical behavior with two different options, UV on and UV off, didn't change that much. And why would be the reason?
Here we introduced the photo active double bond, and with the UV light, it can during the FDM printing, it can form the cross-link structures, and then each layer will be form the covalent bond, and then this material in this direction the mechanical performance will improve because they have the covalent bond. If they just the linear components, then each layer have no covalent bond, so they have the serious isotropic in the mechanical performance in the different directions. For example, the binary, the printing structure or the vectors of the printing directions, they have the different mechanical performance. So we used this, introduce the PBF, they have the double bond, then it can cross-link insert during the FDM printings. So this object of printing object should the much stable flame work even in the water environment.
Yeah. Thank you.
Okay, great.
Okay.
Any more questions? Okay, I have one short question. How far away from your current study towards the final, next step? What is your next step? You have come out with material and you have done some previous study. And what is the next step? Are you going to continue with animal test or short-term animal test or long-term animal test? Which stage you are going to move?
Yes, we try to give more deep research, and we cooperate with the professor in the medical colleges, and we can try to based on if the materials is okay in the in virtual test, and we will try it in the animal test to identify the possibilities for the real practical applications. But it's a real far way to design the biomaterials.
Okay, of course, it's not that straightforward. It's going to be a long journey, and good luck for your this study. Thank you very much. So let's start. Thank you very much, Professor Yang. And the next speaker, we have Professor Xiao from Zhejiang University. He's going to discuss about modeling. And let's welcome.
Can you see my screen?
Yeah, no problem. Great.
Okay. Thank you, Professor Huang, for the introduction. I knew Professor Huang almost since 2015, almost 9 years. So it's now journey. So I was talking something about modeling shaping polymers. In recent years I didn't work too much on SMPs, but still every 2 years I have 1 or 2 paper come out. I think a lot of the audience here are very familiar with familiar with materials, but really don't have very background in mechanics. So hopefully that you will know what is the current progress in the mechanics committee on modeling SMPs. So I think here everyone knows these things. I just need to very quickly go through this one. So for SMPs that we can permanent shape and have temporary shape, normally what we do is we deform at high temperature when the material is soft, and then we cool down to fixed shape, and then you store at low temperatures, the shape will not recover. So if you increase temperature, the shape will recover. So this one is actually finite element simulations here. We normally have 2 types of SMPs that one is called amorphous. The underlying mechanism is glass transition, so everyone knows that one. Last is semi-crystal SMPs, that is underlying mechanism is melting transitions. So I think everyone is familiar with this one. For both amorphous and semi-crystal SMPs, we have something called temperature memory effect. Basically means when the material is programmed at no temperature, it will also recover at no temperatures. When the program temperature is higher, the recovery range also shifts higher. So this effect is actually observed in both amorphous SMPs and semi-crystal SMPs. So if you have this effect, you actually can design something called multiple shape memory effect. The idea is that you have a permanent shape. You can program one temporary shape, cool down, and program a second temporary shape. When you and then cool down again to fix this shape. When you recovers, it will recover to this shape first, and then to the final permanent shape. So the mechanism is quite straightforward. Since you have temperature memory effect, if the 2 programming temperature, the recovery region can be well separated. You can multiple memory effect.
Professor Zhao, sorry, are you showing the first slide? Because we only can see the first slide.
No, I showing.
Okay, now it just moved. We were watching the first slide so far.
Okay, so this one, did you see this one?
Yeah,
okay.
Now yes.
This good? Okay, temperature memory. Okay, so this is multiple shape memory. Okay, I just go through this one. Okay, so can you see the new slides? Two-way. Oh, now I would like to introduce the two-way shape memory effect. For the two-way shape memory effect, is actually only can be achieved in semi-crystal polymers. It cannot be achieved in amorphous polymers. The process is like this. You have a semi-crystal polymers, you deform to a temporary shape, you cool down to no temperature to fix this temperature shape. And now you increase temperature. You cannot increase temperature to very high temperature. If you increase temperature to very high temperature, you will not have to wait. You increase temperature to the intermediate temperature. Now you can have 2 shapes in between these 2 shapes. The problem with two-way shape memory effect is, first, the strain is actually very small, and second, it requires a specific material systems, and also it requires a specific programming process. So it's in fact pretty complex. So nowadays, we have a lot of materials that have get extensively investigated, called liquid crystal elastomers. So in our lab, we actually have do extensively on these materials. It's quite interesting materials. It have something called intrinsic two-way shape memory effect. You have a shape at low temperature, and have shape at high temperatures. So basically, if you have a low temperature, the messaging is have alignment. But if you at high temperatures, the messaging is random directions. So if you heating and cooling, the two shapes can change with each other. Compared with SMPs, the reversible strain is actually very large. We can easily achieve a strain more than 60%, even 100%. If we apply stress, the reversible strain is even larger. And we can easily use the 3D printing technique to fabricate complex structures. For example, like biolayer structures, you can have the two different shapes from 2D to 3D. So I will also talk about something called solvent-induced SME. So the previous slides all show the temperature-induced shape memory effect. For solvent, it's quite straightforward. You have temperature shape.
Sorry to interrupt. I think that, however, the screen seems to still stick to the one page.
Yeah. Maybe you have to put it on the
maybe
presentation mode.
Just use this mode, not a full screen. Okay. Is that work?
I think you should show the whole screen instead of particular window. Share a particular window instead you share the whole screen.
Okay,
my experience is that.
Okay, let me say it again. A whole window. Okay, I see. Maybe I can share just the PPT, right? Something's wrong.
No, share. Somehow it's a setup when you share. Depends on how you share the.
Okay, let me see. How okay, this one work. Well, share this one. Can you see?
And yeah. Okay. Let's try this one.
Okay. So can you see my page? Move.
Yeah.
Yep.
Now it's good.
Okay.
Now it's good.
Okay.
Nice presentation mode.
Okay. Yeah. Okay. So I will give you 1 minute to get through all the slides. Okay. So this is called what is Sichuan polymer? Everyone know it. So this is two different types of SMPs, amorphous and semicrystal. Everyone know it. And this is temperature memory effect. So we good. So programming at low temperature, recover low temperature. Programming high temperature, recover high temperature. If you have a temperature memory effect, you have multiple shape memory effect. Basically means you program the shape at different temperatures, it will recover at different temperatures. So you have multiple shape memory effect. And this is two-way. Two-way is complex. It only occurs in the semicrystal polymers. And actually, right now, the two-way shape memory effect, the strain is very small, 10 to 20%, pretty small. So it's more interesting now. Is people have more interest in something called liquid crystal elastomers. So it's intrinsic two-way shape memory effect. It have a large strain, can come up to 60% to 100%, and the mechanism is different from the glass transition or the melting transition. The mechanism is the lemmatic isotropic transitions. So at low temperature is lemmatic phase, at high temperature is isotropic phase. So if you heating, it change the shape due to the messaging get from the orientation direction to the random directions. So so all these parts is called temperature memory effect, called the heat responsive SMP. You can also have the solvent responsive SMPs. That is, you put a SMP, a program SMP in solvents, it will recover. The reason is the solvent goes into the polymers and soften the segments and induce the shape memory effect. So I think all this is the basic knowledge in the shape memory community. A lot of people who that working SMPs all know all these ideas. The thing is, what is the current progress in modeling? I think for the one-way shape memory effect in most polymers and semi-crystal polymers, we all have very good models. For temperature shape memory effect in most polymers, we also have good models, but we do not have good models for temperature shape memory effect in semi-crystal polymers. We also have limited progress in the past 2 decades on the two-way shape memory effect in semi-crystal polymers. But we can model the two-way shape memory effect in liquid crystal polymers. It's no problem. For the solvent-driven shape memory effect, we can model that in amorphous systems. We cannot model that in semi-crystal polymers. So you can see for amorphous systems, the model is not a big problem. But for semi-crystal polymers, the model is still a big issue. So I will go quickly show how we model these things. Because its mechanics is actually pretty complex, I will only show the mechanism rather than show all these complex equations. So if we want to model amorphous MPs, it's very straightforward. We just need a viscoelastic model. You can have this elastic spring that represent the equilibrium state. This is actually called is represents the permanent shape. Let work. You also have these processes, a spring dashboard that represent the relaxation processes that is account for the phase transitions. So what you need to do is you need to make the this process, the viscosity of the reaction time depends on the temperature. So basically means at high temperature, this dashboard, the viscosity is very low. So the material is only this part, so it's soft. At low temperatures, all these accounts for the stiffness, so the material is hard. So I use one example. The leafen, everyone is a very broad glass transition materials. You have these materials. You have glass transition ranges. We can do some tests called time and temperature superposition, and we can get mass curve for the relaxation modulus. Then we can get the parameter for the model. So now we can model the temperature memory effect. You can see this is different programming temperature and recovery ranges. So the thing is, you can model these things. This is good, but we really want to know why. What do you learn from them? Why they have temperature memory effect? So the model can actually tell you something. If you program the SMP at high temperatures, it's actually the relaxation process with large relaxation time really fix the temperature shape. If you program at low temperatures, is actually the relaxation time relaxation process with smaller relaxation time really fix the temperature shapes, so you can recover earlier. So basically, you have broad glass transitions that is programmed at different temperatures, different processes fix the temperature shape. So that explains the temperature memory effect. It can also reproduce the multi-stage shape recovery. You can see that you can recover at different temperatures. You can the whole recovery process can split to different parts. We also work on the thermoplastics. It's different from thermosets. It doesn't have a very well defined networks, but that does not mean some plastics cannot have a good SMPs, shape memory effect. You can see that these polymers have a TG around 160 degrees C. Even we program it at 205 degrees C, very high above TG. You can see if we program SMP very fast, you deform it very fast and cool down very quickly, you can still have very good, very decent shape recovery performance. But if you deform very slowly, or you deform at even high temperatures, there is a large unrecover ratio. That basically means the permanent shape changes. So it's thermoplastics. We know the permanent shape can be changed at high temperatures. So how can we model these things? The only thing we need to do is we need to get rid of this spring. It does not have a cross-linked network, so you cannot have a well-defined network. So we get rid of this one. You just have these relaxation processes. You can model these things. But we would like to ask, if you do not have a permanent shape, why still have a very high recovery ratio if you program it at no temperatures? So the model can tell you something like this. If you program at no temperatures, these relaxation processes have a very long relaxation time. They act the similar role as the cross-link networks. So these networks, like well-defined cross-link networks, so they can recover, they can fix the permanent shape. So if you deform at high temperatures or deform very slowly, even the longest reaction time, this process can slide. So that is the reason the permanent shape gets changed. Okay, so things get more complex if you go to these cases. If you program in the shape below TG, we know that if a polymer is deformed below TG, the material behavior is very different from when you deform above TG. You have like this complex stress strain curve, like the elastic ranging, yielding, softening, hardening. And we do some tests, and you can see that we can fix the strain and increase the temperature. You can measure the stress. This is called fixed strain recovery or constrained recovery. If you program in the temperature shape below TG, you can actually achieve very large stress, more than 10 MPa. So we typically know the recovery force for shape membrane polymer is really low. Compared with shape membrane alloy, it's very low. So, but if you program below TG, it actually can produce very large stress. So if you want to model these things, this stress strain curve, this constrained recovery for the temperature program below TG, the things become complex. You cannot use a viscoelastic model. So you have to use viscoplastic model. So viscoplastic model, even for the people with a mechanics background, they feel complex because the equation is complex. So I only tell the mechanism. We need two mechanisms. One mechanism is called iron model. So it's actually called a stress-active viscoplastic flow. That means that the polymers have very large reaction time, but if you have a larger stress, they can drive in the plastic flow. So you also need a hardening mechanism. So basically something called back stress. So I don't show equations. The equation is complex. If we have two mechanisms, you can now simulate all this beautiful stress strain curve. You can also simulate the constrained recovery performance. So basically means if you have accurate mechanical model, you can simulate these things. So for the solvent-driven shape memory effect, you need to model two things. The first thing is you need to model how the solvent affects the glass transition. So basically means the introduced solvent can reduce the viscosity. Reduce the viscosity. So you have to define an explicit function of the viscosity dependence on solvent concentration. The more solvent, the soft the material is. So you can see we have this model. We have solvent concentration. You have 3% solvent. The material became soft. But if we do not have solvent dry, it has glassy polymers. So we incorporate the solvent-induced glass transition. But this is not enough for modeling shape memory effect. You also need to simulate the diffusion process. So this is a test of what we do. We have a tube, and we program to this shape, and we put that in the water, and use a camera to record its recovery. So this is our simulation. You can see we model two processes, mechanic process and diffusion process. For the diffusion process for the diffusion process, you can see the solvent on the boundary is increased to the equilibrium one. It gradually diffuses into the middle side. So basically means as the solvent diffuses into the polymer matrix, it softens the materials and the material can recover. So it's possible that the outside is wet, the inside is still dry. So in that cases, you will have no shape recoveries until the inside also have some solvent. You have the shape recoveries. So this is our model and our experiments comparison. So I will spend the last minute to talk about the liquid crystal elastomers. In our lab, we can build a material system, a 3D printing system is a DIW system. We can use them to print liquid crystal elastomers. From the presentation, you can know I'm actually a mechanics person. I didn't have very strong background in material science, but nowadays it's straightforward to build this system. It's not complex. Even for a mechanics person, we can build such a system for DIW systems. The injection of the chemicals from the lasers have some shear force on the messaging. So the messaging is alignment. And use UV light, you can fix this alignment. So you can create some monodomain liquid crystal elastomers. And if you increase the temperature of this substrate, so the substrate is increased, the messaging from the orientation direction immediately go to the random direction, so it can print the monodomain the polydomain LCEs. So basically, you can control the temperature of the substrate. You can print at low temperature. You can print monodomain LCEs. At high temperature, you print polydomain LCEs. You change temperature, you print a multi-layer, you can create complex structures. For modeling things, we just need to introduce the orientation of the messaging into the classic mechanics model, and you also need to model the nematic isotopic transitions. So, we can use very phenomenological equations like this one to model these transitions. Basically means that at high temperature, it's a random direction. At low temperature, you have orientations, and we fix the strain, and we can get the parameters. Then we can implant the model into the finite element suite. You can see this is a two-layer structure. One layer is monodomain LCEs. Another layer is the polydomain LCEs. You have this directions, the direction for the messagings. This is the direction in this direction. This is the orientation in this direction. And from the shape, you can really tell the difference. The two looks exactly the same, but if you change the temperature, the two have very different shape changes. That is, you can control the orientation of the messagings. You can create very complex structures. Okay, so I will do the summary. So in the past 10 years, we have developed many models for shape memory polymers, but mostly for amorphous polymers. We don't tackle the semi-crystal polymers. And we model glass transition for shape memory effect. We can model temperature memory effect. We can model the solvent-driven shape memory effect. And in the past 2 or 3 years, we begin to work on LCEs. We can use LCEs to create complex structures. We can see that LCEs is really an intrinsic two-way shape memory polymers. With that, I'll thank you. Questions?
Okay, thank you very much, Professor Xiao. And any question? Yeah, so
Yeah, may I have a question?
Sure.
Thank you very much for your presentation. It was very interesting and I learned many things myself. In general, if there is a new type of shape memory polymer we develop in our lab, for example, combination of different materials with the different TGs and stuff like that, what you need as a person do the simulation as an input for modeling, and what we expect as an output from your model. I mean, I try to find the way to understand the application of this simulation for developing future products.
Mm. So for amorphous systems right now, we can it's easy. You don't need our model. You just use Abacus or the commercial file element software. You can model the supplementary effect. It's not complex. The only thing you need to do, you need to do a temperature sweep test, a time temperature superposition. You need to get the basically you need to either use the small strain dynamic test to measure the sludge modulus or the function of the frequency. You do multiple temperatures, or you can use a stress reaction test. You apply very small strain at different temperatures, and then use the time temperature superposition. You construct mass curve, and from this one single test, you can get all the parameters for our model. Then what you can do? You can predict all these shape recoveries that you program at different temperatures, and what is the recovery ranges, and what is the onset temperatures, and what is final recovery temperature. This is all no problems. The really useful for the final element is you do the complex structures. So if you do a small specimen, you don't need file element, right? You can do experiments. You can easily get all the information. You don't need file element. But if you want to do a complex structures, a file element may help you to design the shapes. So that is the reason we use file element. So I think whether a model can be used is really because it needs to be simple. It cannot be very complex. Even the people have not from the mechanical community, they can use it. That the model will be useful. Otherwise, only the mechanical person can use it. It will not be very useful, especially for design. Yeah.
Yeah. Okay. Thank you very much.
Thank you. So now we have a question from Taoxi. Taoxi, are you here? You can ask directly now. Yeah. Okay. So the question here is this: for the case of programming. Okay. His micro is dead. For the case of programming below TG, where the shape fixed ratio be good since there is no phase transition during the whole process.
Okay. Programming below TG is you have two ways. One way, you program below TG, you unloading, you get a temporary shape. And in this process, of course, you have some you cannot have very high shape fixity because you unloading, some strain just recovers. But you can also deform below TG, you cool down to even lower temperatures. In these cases, you can fix almost all the shapes. It's not a big problem. You still can fix good shapes. So I think it's really depend on your procedures. If you direct unloading, the shape fixity not good. But if you deform it below TG, cool down to even lower temperature, you still have good shape fixity and have good shape recovery. Yeah.
Okay, good. So we have about 2 minutes. Not any other question? Okay, now I have a small question. For PCL, I'm cross-link the PCL. If we deform it, program it at high temperature, the deformation mostly is plastic. But if we program it at room temperature, it actually significantly stretched. And then our heating is able to almost fully recover. So can your model simulate this kind of phenomenon? And cross-link PCL, this type of thing.
Yeah, if it is amorphous, no problem. If it's semi-crystal, we can still model it, but the model is more complex. I don't want to do it because I hate semi-crystal polymers. You have to always track all the phase the new phase formed, and the phase melt, the crystal phase melt. It's complex. You do tracking every steps. So I don't want to do it. But for the amorphous polymers, it's easy. I think PCL is semi-crystal, right?
Yeah, actually, it's a phase kind of transformation upon stress-induced kind of hardening.
Yeah, that's complex. Yeah. But I think the mechanism is the same, right? If you have deformed high temperature, basically we have no network to fix it. But if you deform low temperatures, there is some species there that act a similar role as the cross-nuclear network. Yeah.
Okay. Yeah. Exactly. Time. Thank you very much.
Thank you.
Anything to?
Yeah. Thank you very much. I see there is one more question, but I would ask Ali, please send your question directly to Prof. Xiao. Maybe he can answer you separately because we are end of the meeting now. I would like to thank everyone, the speakers specifically. Thank you very much for being in this webinar and also for your presentation. I would like to also ask, thank you, Professor Huang, for actually managing this webinar and also for the invitation and everyone who attended in this meeting. After this meeting, we are going to share the record as a video with everyone in the channel of webinar, and I would invite you to follow our LinkedIn page for the future webinars. And this webinar is going to be every 2 months, and we are going to invite more and more people, and they will share their research and studies with us in future. Thank you. Have a good time, everyone.
Bye-bye.
Thank you very much. See you next time.
See you.
Bye.